20. So after the first mini course. I don't know if everyone received the message, but there will be a boat trip on Saturday morning for those who are still here. So it's gonna be from 10 o'clock on. And it is departing from Gloria, Marina da Gloria, and going until these islands on front of Ipanema Beach. So it should be a very nice trip. It's going to be 40 reais contribution of each person who wants to do it. And other than that, all the announcements are going to be made in this panel here in this second floor. So, or you can, if you have any questions, you can ask either Claudio or myself, or Augusto if he's around. So it's my pleasure to present Hugo, Duminil-Copin, who's gonna give the first mini course this morning, together with Vincent Tassion, who's gonna give the third, fourth, and fifth lecture, right? Okay, so the title is on the board, and okay. Thank you.
Well, thank you very much. It's a pleasure to be here to give this mini course. I see that some people were in Vancouver as well, so for them it's going to be absolutely nothing new. For the others, I hope I will present a few new things. I'm basically going to do all the nice part, and then Vincent will have all the dirty part to do. So if you want to complain already, just complain to him. Yeah, so what we thought we would present in this mini course is a recent result, which we believe enables us to understand a little bit better what happens with what we call Sharpe threshold in statistical physics. So I will explain to you what it is and what we mean by that. But in order to maybe not dive directly into the most recent result, which is a little bit harder, of course, than the previous ones, what we thought we would do is try to have the Bernoulli percolation model as a silver line that we are going to follow basically for the whole week. And the goal would be to every single time explain to you what happened for Bernoulli percolation, what was the history there, and what was missing to understand what now we understand. So today is going to be typically this kind of philosophy. We are going to discuss only the two-dimensional case. So we are going to discuss 2D percolation type models. And we are going to start by Bernoulli percolation, try to give you a definition of what it is. I mean, hopefully succeeding at giving you a definition of Bernoulli percolation, try to give you a motivation, and try to explain that there something happened that people were first understanding the problem at hand a little bit like just by doing technical things, by moving their hands, but not having a general understanding of the thing. And then happened a breakthrough, which is not due to us at all, which was the introduction of discrete Fourier analysis and the theory of Sharpe threshold to solve the problem. And I want to explain to you how you solve the problem using this thing. And then the third step that I will explain today is how this general theory of Sharpe thresholds extends to a much wider family of models. And that was really before the first techniques that were a little bit with your hands. They do not extend at all. So you are bound to work with Bernoulli percolation. But once you understand that Sharpe threshold theory just gives you your results, this more general theory extends to a much wider class of models, as I said. And tomorrow, starting tomorrow, what we will do is that tomorrow I will explain to you what happens in higher dimension, which is the more interesting dimension for us. So try to first do with hands, exactly like people did in 2D. So that will be my lecture tomorrow. And after tomorrow, Vincent will start to explain to you how you do Bernoulli percolation in higher dimension, not with hands, but with the theory of Sharpe threshold, and how you extend it. So I hope today is going to be some kind of snapshot, a 2D snapshot of what will happen with the 4 next lectures. So today it's going to be 2D percolation. So as I said, we will start with the simplest model of percolation. So we take the lattice Z2. So it's just a graph where whose vertices are the integer coordinate points in Z2, in R2, sorry. And you have edges between nearest neighbors. By the way, I will very often use, and I hope that Vincent will stick with this definition. It's good to come first because you can fix all the definitions you want. Even you can, be a little bit nasty and put those that you know later will be very unpractical. But so this one, I don't know whether it's going to be bad for you. But so x neighboring y. This will be if xy is an edge of Z2. And Bernoulli percolation is simply a percolation of random subgraph of Z2. So omega will be, I will encode this random subgraph by looking at configuration which are just functions from the edges of my graph in 2, 0, 1. And I will think of it as a graph. So think of it as a graph with vertex set would be just Z2, so all the vertices of the original graph, and the edge set of omega would be the set of edges in Z2, such that omega E is equal to 1. We call them usually open edges, so probably we will use this. So open edges for 1 and closed edges for 0. So you have omega, think of it either as a function from the edges or as a graph, a random subgraph, at this point, a subgraph of Z2. Now I want to sample one at random, and what I will do is the simplest thing ever. I will just say that omega E is a Bernoulli random variable of parameter P, where P is between 0 and 1. And they are ID, in the sense that they are independent for different edges. Okay, so you take a collection of ID Bernoulli random variable of parameter P, and I will denote the law, so this kind of product measure law, by P of it's a summer school, so you can ask questions. I will defer all those that I don't want to answer to Vincent, and the other one I will gladly answer them right away. Okay, so this is the measure for now I have a random subgraph of the plane. And the main question that we are interested in is the connectivity properties of this random subgraph. So the first question, which is natural to look at, is whether this graph is connected or not. So all the vertices are connected together. But it's very easy to see that as soon as P is smaller than 1, strictly, almost surely your graph will not be connected because every single vertex has a positive probability of having four edges which are closed around it. So this is not the most interesting question when you look at this type of model. So what is the next one? Well, the next one will be, okay, maybe I cannot be connected, but maybe I can have infinite connected components. And that will be the main question, is do I have or not this infinite connected component? And the answer is that there exists a critical point, PC, which is a priori between 0 and 1 at this stage, such that if P is smaller than PC strictly, then the probability that there exists an infinite, or let's say 0, is connected to infinity. So that would just mean 0 is in an infinite connected component. This thing is 0. So if the parameter is below my threshold, it's 0. And if it is above, then it's strictly positive. Okay? So the existence of this value PC is due to the fact that if you think about it for a moment, you will see that this quantity is increasing. Maybe I don't want to do it because anyway later on it will follow directly from what I'm doing. So if you never saw Bernoulli percolation you are maybe already lost because you are wondering why there should be a PC like that. Maybe it could oscillate between phases of P for which this is 0 and phases of P for which this is positive. But for this one, for these people, just wait for me for like maybe 30 more minutes, and I will just write basically the differential of this quantity. So you will see that it's positive. And for the others, you are already bored, so that's perfect. So I apologize for people who already saw that, but I want to have as much as possible everybody on board. So there is a critical point. So if you are a little bit like you have the fiber of mathematics, like you live mathematics, the first thing you want to do is to compute this quantity, right? And here is somehow the theorem, which I want to discuss. I mean, I will mostly discuss this theorem today. It's a theorem which is due to Kesten, and it says that PC, well, it's exactly equal to 1/2. So it's basically the simplest number you could imagine. I mean, okay, maybe that can be discussed, but one of the simplest, at least, number between 0 and 1. Okay, that was not how he guessed it. And actually, he didn't guess it. He proved it. But, well, the first people who guessed it, it was a little bit like that. It was really like, oh, come on, a number between 0 and 1. Give me 1. Okay, 1/2. Yeah, that must be 1/2. Okay, so how do you prove that? So first, yeah, how do you prove? I mean, why would you prove this? Maybe I should say. It's interesting to have the critical point, the value of the critical point, because the main point that I didn't mention here is what is happening at the critical point. That is what physically or mathematically you are interested in, is understanding how you pass from the phase where you have only finite connected components and the phase where you start to have infinite connected components. You want to understand exactly this passage from one to the other one. In order to understand what is happening, it's definitely simpler. Maybe it's not sufficient, but it's going to be the first step is to understand where it's happening. So actually, here we are lucky enough. We know, I mean, you will know in 1 hour, if you listen well, why it's happening at 1/2. You will see actually that starting tomorrow, we will start to have information on how these things are happening in higher dimension without knowing where PC is. But this is a priori harder. If you can avoid having to go through all this trouble of not knowing where PC is, try to do it. So today we are going to try in 2 dimensions. We can compute PC, so let's try to do it. Okay. So in order to understand that PC is equal to 1/2, the first thing to observe is that there is some kind of symmetry between P and 1 minus P in 2 dimensions. And this symmetry is the following. So let's imagine I have Z2. I will not make the same mistake as in Vancouver, where I did a way too big picture. So here, let's take 4 faces. So this is Z2. And let's pick the dual graph of Z2. So what is the dual graph of Z2? It's just you put a vertex in the middle of every face, and you put edges between nearest neighbors. So you obtain again a square lattice just translated by 1/2, 1/2. Okay, so the dual, which I would denote like that, is simply 1/2, 1/2 times Z2. So take this graph, and now for every, no, that is not a good color. Take this one. It's maybe not better, but anyway. For any configuration omega, let's take this configuration, say, I can associate, so for any omega, I can associate a configuration on the dual lattice. So how do I do it? Well, what I will do is I want basically that for every edge which is not present in the primal lattice, I want that the corresponding edge, there is always a corresponding edge, there is one unique edge of the dual lattice intersecting it. I want the corresponding edge to belong to omega star. So if you denote, if say this is E, and the associated edge is E star, I want basically that omega star of E star is equal to 1 minus omega E. I want, if this edge is not present, then this edge should be present. And in order to make things symmetric, if this edge is present, I don't want this edge to be present in my dual configuration. So you have a natural dual configuration which looks like that. Okay, if omega is Bernoulli percolation, I mean the law of omega is Bernoulli percolation of parameter P. What is the law of omega star? Well, every edge is open with probability 1 minus P, because that's exactly the probability that the corresponding edge of the primal lattice is closed. So every edge is open with probability 1 minus P, and the state of different edges is independent simply because they depend on the state of different edges of the primal lattice, which are independent themselves. So what did I conclude is that if omega is sample according to this, then omega star is sample according to Bernoulli percolation of parameter 1 minus P. Here I'm cheating a little bit. It's on a translated lattice, but I think that it will not lead to any confusion. Okay. So if you do that, now there is a natural thing that you can think of is to try to see, imagine for instance, so you have 1/2 here, which is, by the way, the self-dual point, is the point for which P is equal to 1 minus P. Imagine for a moment that PC is smaller than 1/2. If PC is smaller than 1/2, then what happens? So you have a first, here you have no infinite cluster in omega, and here you have infinite cluster in omega. By the way, I didn't tell you because we won't use it, but here when you have that 0 is on an infinite cluster with positive probability, in fact you can prove that there exists an infinite cluster somewhere with probability 1. And this you can just see because of ergodicity. Yes? So what I just said, so I'm saying, here what I prove is basically that there exists an infinite cluster with positive probability. I'm also saying it's actually connected to 0. But what I'm saying is that as soon as there exists somewhere an infinite cluster with positive probability, in fact it happens with probability 1, just by ergodicity. All these things are IID, so you can use any ergodic theorem you want. Or even it's just a tail event, so you can use Kolmogorov law. It works very well at this point. Okay, so here you have no infinite cluster. Here you have infinite cluster. But there is also PC, 1 minus PC. And in the dual, what do I see? So I see that here, if P is larger than 1 minus PC, then 1 minus P is smaller than PC. And therefore, in the dual, I don't have an infinite cluster. So here there is no infinite cluster in omega star. And here, there is infinite cluster in omega star. So what I want you to observe in this case is that there is a whole range here, which is this range, where you both have an infinite cluster in the primal model, so in omega, and one in omega star. And that, if you think about it, think of the infinite cluster as being a huge C with small islands of small finite clusters. Well, then it looks a little bit strange that you would have both a huge C and a huge dual C, if you want, a huge land. Think of omega star as being the land. And that just seems impossible. The coexistence of an infinite cluster, I will answer in 2 seconds, of an infinite cluster and an infinite cluster in the dual. And indeed, if you know a little bit of percolation theory, you can prove that this doesn't occur. Yes?
But you need to take into account that if the
Exactly. So that's the word I didn't want to say, but yes, indeed. So how you would prove that this cannot occur? You would prove by proving that, in fact, the infinite cluster, when it exists, not only it exists almost surely, but it's also unique. So it's really think of a C that it's almost everywhere. And the dual cluster, if it's also unique and it's a land which is almost everywhere, and that in a translation invariant way just cannot happen. You can just see in 2 dimensions that you cannot have coexistence of these 2 C's if you want, because just it will have to strip into an infinite number of clusters. So you can prove it. We won't prove it that way anyway, so I don't want to go into that direction. But at least heuristically, it seems indeed unlikely that you would have both an infinite cluster and infinite dual cluster. So what does it mean here? Heuristically, it means that PC should be larger or equal to 1/2. Again, this is a physical argument at this stage. There is nothing bad with physics, even though every single time I will mention it in this class, it will be to say that this is not sufficient. But so this is a physical argument for PC larger or equal to 1/2. Now let's assume that PC is strictly larger than 1/2. Then if you do the same thing, what will you have 1 minus PC, which is here. What will you find? You will find a whole range here of P for which you have no infinite cluster in omega and no infinite cluster in omega star. So there, again, it seems a little bit weird because how could it be like if you don't have an infinite cluster in omega, it seems to be saying that then in the dual you should have really this C of this infinite cluster, which is kind of fragmenting the space into small clusters for omega. So one has to be careful here. There is no topological obstruction in having no infinite cluster in omega and no infinite cluster in omega star. So for the people who think that here, well, if you don't have an infinite cluster in omega, necessarily you have one in omega star, it's not the case, simply because you could imagine to have concentric clusters like that. Etc., until infinity. So there is no obstruction, but the fact that it happens really on a whole interval seems to be a little bit unlikely, because imagine you have such a picture here at some P. At some value of P, you have really your finite cluster in omega, surrounded by a finite cluster in omega star, surrounded by a finite cluster in omega, etc., etc. When you are going to change P, let's say you decrease P, then the clusters in omega should be smaller and smaller, and the clusters in omega star should be bigger and bigger. And then it seems that maybe, actually, you could imagine that if this is a drastic change, like really the cluster in omega becomes much smaller and the clusters in omega star becomes much bigger, maybe if at some value of P this happens, this cannot happen for smaller values of P. Somehow, this is kind of an equilibrium point where there is exactly balance between the dark side and the, okay? And then, if you change a little bit, boom. If you decrease a little bit P, then omega loses completely. So all the big clusters of omega start connecting and make a huge infinite cluster. So this is already harder to understand that this regime, but it's also trivial for physicists, that this cannot happen at more than 1 point for percolation, and therefore that PC should be smaller or equal to 1/2. So this is really heuristic. So what we are going to try to explain today is that you can change it into a proof. Okay? Okay. So first thing that we are going to observe is that at 1/2 there is something special happening. We said 1/2 was the self-dual point, the point for which P is equal to 1 minus P. Let's try to harvest that in some clever way. So lemma look at the following. Take a box of size n times n plus 1. And let's look. I should be maybe consistent in the colors. Okay. That is not going to be easy. I'm used to blue and red. Let's change to blue and red. Okay. So red is going to be omega every single time, and blue will always be omega star. So let's look at the probability that there exists a path of open edges going from the left side to the right side of a box of size n times n plus 1. Think n times n. Okay, think a square. And let's look at this probability at 1/2. Do you know to what it is equal to? Let's see whether you are a good physicist first. And so that somebody who didn't see it before has an idea what this is equal to at 1/2. Okay, I lost already everybody. That's perfect. Now I can say whatever I want. Sorry? So what is the simplest number between 0 and 1? So this is equal to 1/2. Don't worry, I don't have any fixation on 1/2. We will see other numbers in the week. But this is equal to 1/2 whatever n. So for every n, this is equal to 1/2. And I think this is one of the cutest arguments I know in mathematics, so I will try not to destroy it completely. People told me this was confusing. This is the beginning of a proof, and you will see what happened at the end of the proof. I don't want to. Somebody came last month after like 2 hours of talking. Yeah, I understood basically everything, but what is this weird phase? So, okay, beginning of proof. So the idea is going to be the following. Imagine you don't have a crossing from left to right. So there is no path from left to right. So if I draw the clusters like that, none of these points is connected to the right. Now let's draw the dual lattice. So the dual lattice has edges like that, of course. And edges like that, etc. And edges like that. Every edge here, if I look at the right boundary of my clusters connected to the left, what do I see? Well, I'm blocked by edges in the dual lattice doing like that. Open edges in the dual configuration blocking the clusters from the left to go further on the right. But this creates to me exactly one path from top to bottom in this rotated version of my original box. Because these edges are irrelevant here. If you think about it, that they are open or not is not relevant for you. These edges, same thing. So here, the dual of my box, the dual of this box, is exactly a rotation by pi over 2 of the original box. So what did I prove? I proved that the probability at 1/2 of crossing my n by n plus 1 box plus the probability of its complement is equal to 1. But the probability of its complement is the probability that in this box, which also has size n times n plus 1, I have a crossing from top to bottom. And this is also at 1/2, but notice that this is just Bernoulli percolation of parameter 1/2 as well. Therefore, the probability of the event and its complement are equal, and I get what I want. Okay? Very well. So this is for a box. Basically, you understand the n plus 1, because if you take a n by n, you end up with a n by n minus 1 times n plus 1 on the other side. It's a little bit... So this is just to have a self-dual, but basically it tells you that crossing a square is probability 1/2. Is it a specialty of the square? Is it a specificity of that, or do you have this property basically for any shape, say? Well, you can try, for instance, to look at it for a rectangle, n by 2n box. Then you know it's smaller than 1/2 if you want to cross in the long direction, but does it go to 0? There is a theorem that I'm not going to prove, which is due to Rousseau, Seymour, and Welch, and which tells you that, in fact, whatever the shape, the probability of crossing remains between 0 and 1 uniformly in the size. So so for every rho positive, there exists a constant, it's depending on rho, such that for every n, the probability at 1/2 of crossing n by rho n box. Okay, it took me exactly 2 seconds. Ah, no, here. N by 2n. Of course, it's bounded, it's bounded by a constant, 1 minus a constant and larger than this constant. So the important thing is the uniformity in n. You cannot have a uniformity in rho if you think about it. Obviously, when you get longer and longer, for instance, you need to cross squares every single time. So, of course, you don't have a uniformity in any shape, but for a fixed shape, 1 rho, for instance, you have a uniform constant. So that is going to be the one of the 2 big black boxes today, in the sense that I'm not going to explain how you prove that. And you are welcome to ask Vincent, who will spend hours explaining to you how it is. No, Vincent saved himself a few years ago by finding a short proof of that. So I think he was expecting that I would send everybody to him. So he can explain to you in like 30 minutes how he does it. Okay. So this is my black box. Now, how do we deduce, say, for instance, that PC has to be larger or equal to 1/2? Maybe heuristically you kind of understood that this one was maybe simpler than the other one, because the coexistence of 2 infinite clusters, it looks less fishy than this weird argument that I was trying to highlight, that maybe if you change the values of P, blah, blah. The first one, just absence of coexistence, seems a little bit simpler. And indeed, this inequality is simpler. So corollary of this, for instance, there exists a constant, alpha, positive, such that for every n, the probability at 1/2 of 0 connected to the boundary of the box of size n, so this is going to be lambda n, is going to be from now on minus n to the d even. I think it will use the same notation in higher dimension. And this is the boundary, so it's exactly the point at distance exactly n of the origin for the infinite norm. This is smaller than 1/n to the alpha. In particular, we deduce, so this, let's call it 1. In particular, we deduce that the probability at 1/2 of 0 connected to infinity is 0. Just let n go to infinity. Okay. So, let's prove that. What is the probability that, say, you cross from distance n to distance 2n? What is the probability of having the path from inside to outside? So it's difficult to compute explicitly, but can we bound it by something which is not close to 1? Okay, so if you don't have that, this is exactly, if you have that, it's exactly the probability, if you don't have that, it's the probability that there is a circuit in the dual configuration which surrounds the small box. Think of exactly the same reasoning as here. Take the clusters connected to the bottom, to the inside box, its exterior boundary is just a circuit in the dual configuration surrounding the small box in the big box. So this, you can estimate it by doing the following. So the probability of having this path, what you can do is you can fix this rectangle here and ask that you have a crossing from left to right. Okay, it's a very nice n by 4n box. So this happens with probability C of 4. So this probability C of 4, I get that. And I can ask exactly the same here. Okay. So for people who know the FKG inequality, you can also do it here and here, and just say it costs me, again, C of 4 and C of 4. But, okay, you see these 4 events, they are not independent anymore, right? The event that you have a crossing like that is not independent of the event that you have one like that. But for those who know the FKG inequality, you know they are positively correlated. So the probability of the intersection is larger or equal to the probability, or to the product of the probabilities. I don't want to mention the FKG. I mean, I did mention the FKG inequality. I don't want to use it really here. So what I want, I'm going to just do something even simpler than that. Condition on the lowest crossing like that. What is the lowest crossing in this case? It's just the boundary of the clusters touching the boundary, right? The cluster of the primal graph touching the boundary, right? Take the lowest path like that. Take the highest there. So when you condition like that on this highest and this lowest one, what is the information that you have on the state of edges in between? Well, you have exactly 0 information. I didn't tell you anything about the state of the edges here. In order to, for instance, declare that this is the lowest path, I need this path to be open in the dual configuration. And I need below, if you want, not to have a lowest path, a lower path. So really, it's measurable in terms of all the edges which are on this path or below. Same thing here, on this path or above. So in between, you have no information. But that means, this is good for us, because that means that here, in this area, I just have Bernoulli percolation, except maybe on the boundary, but on this area, I have Bernoulli percolation of parameter 1/2. So I can ask to have a crossing from there to there. And obviously, having a crossing from there to there is simpler than having a crossing from there to there, because it's a smaller area. So of course, the probability of this additional crossing is going to be larger than C4. And if I do the same on the other side, I will also get larger than C4. So the probability of this is larger than C4 to the power 4. Okay. So it's a constant. So in particular, I have an upper bound on the probability of having a path from the inside to the outside in this box. Okay. But now what I can do is, if I want to have a path from, say, 0 to distance 2 to the n, or 2 to the k, sorry, then I need to have a crossing between 2 to the j and 2 to the j plus 1 for every j smaller than k. So this probability, and it happens in disjoint annuli, therefore it's completely independent. So this is smaller than the product for j smaller than k of the probability at 1/2 of having a path between 2 to the j and 2 to the j plus 1. But I just bound that by 1 minus c of 4 to the power 4, this is smaller than 1 minus c of 4 to the power 4 to the power k. Okay? So if you fix n to be 2 to the k, here I have a bound which is polynomial in k. So this is something like n to the log 1 minus c4 4 divided by log 2, if this is n. Okay? So you have a polynomial bound, and in particular, the probability of having an infinite cluster is 0. So of course, I mean, I kind of hide the difficulty in this theorem, but that's, well, yeah, it's completely dishonest, but that's fine. It's not such a difficult theorem, but anyway, it's a fundamental one. Okay, so we have one bound. We know that PC is larger or equal to 1/2. How do we do the other bound? So this bound, by the way, was known for a very long time. It goes back to Harris. So many years before Kesten proved his PC equal 1/2 theorem. So the other bound is the difficult one. So how do you get the other one? Well, the idea is going to be, so I need to prove that above 1/2, I have an infinite cluster, right? Like that, if for any p larger than 1/2, I can prove there is an infinite cluster, I just prove that any p larger than 1/2 is larger or equal to PC, and therefore PC must be smaller or equal to 1/2. Okay, so what I can try to do is I can try to prove that these quantities, okay, they are bounded, but maybe they actually tend to 1 as soon as p is larger than 1/2. Exactly the heuristic I was trying to tell you earlier is that, okay, if at 1/2 it is balanced, maybe that's the only value where it can be balanced. And in other way, it's kind of natural to expect, indeed, that this quantity, when I draw the graph of this function, p gives the probability. So if I draw P gives this probability, say for a box of size 2n or for a box of size n, say. So we have P gives a probability, let's say rho n. It's natural to expect that the graph of this function starts obviously at 0, ends at 1, is somewhere here at 1/2. But it's kind of natural to expect that it looks like that. It stays close to 0 for a very long time, then goes very quickly close to 1, and then ends its life at 1. Meaning that there is a very short window, if I fix epsilon and 1 minus epsilon, there is a very short window of values of p for which, that is not such a short one, but anyway, for which the function is staying between epsilon and 1 minus epsilon. If I can prove that indeed there is a short window, and in addition, if I can prove that this window goes to 0 when n goes to infinity, so you get closer and closer to a step function, then this will kind of tell me that this thing above 1/2 has to tend to 1. And maybe if I'm lucky enough, I will even have a speed of decay, the speed of convergence to 1. So this thing is called a sharp threshold for the function. The function undergoes a sharp threshold. This notion didn't appear in physics, surprisingly enough. It appeared in combinatorics. When you try to study the graph properties of random graphs. For instance, if you look at the Erdos-Renyi graph, that's maybe where it appeared first. And it is really a finite size version of the notion of phase transition in physics. Think of the following. I told you that the existence of an infinite cluster has either probability 0 or 1. So think of a big box and think of whether there is a big cluster in this thing or not. when n goes to infinity, this should tend to either 0 or 1. If there is an infinite cluster, there should be a big cluster in my box, simply because the infinite cluster should intersect this box. And if there is no infinite cluster, then a fortiori there should be, it should also tell you that the clusters are small, and therefore in the box you won't have big clusters. Well, here, at fixed n, the probability of not having an infinite cluster is not 0, it's not 1. Of not having a big cluster is neither 0 nor 1. It's a certain function between 0 and 1. So in finite volume, you cannot say that it's either 0 or 1. It's going to be either, you want to say that it's either close to 0 or close to 1. And when p varies, there is a value where it's going to be roughly 1/2. So a phase transition, somehow what I'm trying to say, and which is not clear at all, I realize, but that's okay, is that a phase transition in infinite volume, kind of already in finite volume, you should be able to notice it by the fact that certain properties of your graph should undergo a sharp threshold. So it's a finite, if you want, finite version of a phase transition. So here, if I manage to convince you that this quantity undergoes a sharp threshold, then probably it's already a good sign that at 1/2 you should have PC equal, you should have PC equal 1/2. So my goal now is going to try to prove to you the following. Proposition is that there exists, for any p larger than 1/2, there exists a constant c such that, actually let's even make it not depend on p, such that the probability, and I'm going to take one example because that's the one I'm going to use, but I could do it with any shape, so let's set n times 2n. The probability of this event, the event of crossing, now tends to 1. And tends to 1 larger than 1 minus n to the minus c, p minus 1/2. For every n. So it goes to 1, and it goes to 1 fairly quickly. In fact, if you would take p smaller than 1/2, you would have the same result with smaller or equal to n to the minus c, p minus 1/2. Okay? But before I prove this proposition, let me tell you how you conclude. How you conclude that PC equals 1/2. Like that, you can just go back to sleep. And so how to conclude? So corollary, PC is smaller or equal to 1/2. So how do you do that? Well, what you are going to do is you are going to construct by hand your cluster. So take a box of size k times 2k and ask that this box is crossed. Okay? So what is the probability of that? So let's call this event A0. Probability at P of A0, so fixed, of course. P larger than 1/2. So probability of A0 is larger or equal to 1 minus k to the minus, and this constant, let's call it alpha. Let's call it alpha. Minus alpha. Now let's look at A1, which is the event that the box of size 2k times 4k is crossed like that, in the hard direction. Probability of A1 is larger than 1 minus 2k to the minus alpha, etc., etc. Define AJ to be the event, so if j is even, it's the event that 2 to the jk, 2 to the j plus 1k is crossed in the hard direction. If j is odd, it's going to be 2 to the jk times 2 to the j plus 1k crossed in the hard direction that way. Okay? Okay, what is the probability in this case of aj? Well, it's larger than 1 minus 2 to the jk to the minus alpha. Okay? So what is the probability of the intersection of all the aj? Well, it's larger than 1 minus the sum of the errors. So the sum of 1 over 2 to the jk to the alpha for j larger or equal to 0. So if I fix k to be large enough, this quantity is a nice quantity smaller than 1/2, say. So for k large enough, this is larger than 1/2. So what did I prove? If you have this intersection, I just proved to you that the box of size k is connected to infinity. Right? Because if I have the intersection of all these things, I have an infinite cluster. So I just proved that this thing is larger or equal to the probability of having an infinite cluster. I didn't tell you that it is connected to 0, but as I said, this is sufficient just by union bound. If the box of size k is connected to infinity, then one of the points is connected to infinity, and therefore the probability that 0 is connected to infinity is larger or equal, so that I have, like, say, k points on the left, so one of these points is connected, and therefore I get this. Okay? Since I did that for every p larger than 1/2, I did use that pc is smaller or equal to 1/2. Okay, so if I have this thing, I'm done. Notice that I didn't really need this decay. Right? Because I just need this sum, the sum of a functional of the 2 to the jk, to be summable. So sum of this to the power alpha is obviously summable, but if I would have basically anything better than 1 minus 1 over log n, I would also be happy. Okay. So here we are. We need to prove that our crossing probabilities undergo a sharp threshold. And how do we do that? Well, we are going to do that by proving, imagine, let's do a parenthesis. Imagine I have a sequence of function fn. They go from 0, 1 into 0, 1. And imagine that, or if let's say I have one function f. Imagine that f satisfies the following differential equation. F prime is larger or equal to a constant k times f 1 minus f. Okay. I want to bound the size of this window. I want to try to prove that there is something like that when I have an inequalities like that. So here it's a computation which is important because we are kind of going to use it several times in the class, or at least the intuition. f prime larger than k f 1 minus f. So what do? I want to integrate this. I want to say, okay, fix p such that f of p is 1/2. And I would like to understand at p plus epsilon and at p minus epsilon, what is the value of f? I mean, can I bound these things? So in order to do that, I'm going to integrate this inequality. So this inequality written like that is maybe not that clear, but f prime divided by f1 minus f is what? It's nothing else than the logarithm of f over 1 minus f, which is differentiated. So it's a derivative of the log of f over 1 minus f is just f prime divided by f1 minus f. So this thing is the same as this. Okay? But if I integrate this between p and p plus epsilon, so if I integrate this between p and p plus epsilon, I get that f of p plus epsilon over 1 minus f of p plus epsilon is larger or equal to e to the k epsilon times f of p over 1 minus f of p. Okay? So this f of p over 1 minus f of p, since I chose f of p to be 1/2, it's just 1. This is smaller or equal to 1. So what did I get from that? I get that 1 minus f of p plus epsilon is smaller or equal to 1 minus exponential, exponential of minus k epsilon. And therefore, it tells me that f of p plus epsilon is larger than 1 minus e minus k epsilon. So if k is large, f of p plus epsilon is very close to 1. In the other direction, I let you do the computation yourself. You get that this is smaller than e to the minus k epsilon. Okay. And notice that here, if f of p is not equal to 1/2, but set to a constant, that change not, like here it's just going to change that this is not exactly 1/2, but it's just going to change that here you have a small constant in front, a big constant in front. So my point is that the whole goal of these lectures is going to be to try to find differential inequalities of this type for f of p, which is just crossing a box of size p, a box of size n. Or we will see tomorrow, I mean starting tomorrow and in the lectures of Vincent even more, we will see also, for instance, maybe apply this to 0 connected to distance n. So we will try to obtain this type of things. Because our goal, for instance, if you think of, if you look at this type of inequalities and you try to get this from the fact that at 1/2 it's equal to a constant, this, I mean it's larger than a constant, you notice that here in the case of crossing probabilities, so if we define fn of p to be the probability of n times 2n crossing, then here to get this, we need to prove that fn prime is larger than constant log n times fn 1 minus fn. Right? So today, for instance, I will explain to you how you get that. Okay. So how do we get that? First, there are two small things that I want to discuss on this inequality. The first one is that this term is very natural, simply because when the probability is close to 0 or close to 1, the derivative cannot be large. You cannot have a large derivative uniformly between 0 and 1. So this fn 1 minus fn is telling you that the lower bound on fn prime cannot be good when fn is close to 0 or to 1, which is very natural. Second thing is that fn is the probability of an event. So this thing is in fact nothing but the variance of the indicator function that you have a crossing. Right? If you look at the indicator function of this, you take the variance, you are going to get the probability of this minus the probability squared. And therefore, you get fn times 1 minus fn. OK, so we want to get a lower bound on the derivative in terms of the variance of your function. So what I'm going to do now is explain to you something more general than just this function. It's going to be something that depends on, I mean, which is applicable to a large variety of what we call Boolean function, which is how you express this in terms of what we call inference, and how you bound from below the inferences in terms of the variance. Okay, so it's a kind of detour, but it's a very important one. It's a very bright observation that you can use the theory of sharp threshold here. So define, it's not due to us, this observation. That was not just, OK, so let f be a function from 0, 1 to the n into 0, 1. Maybe let's define it as x because I don't want to confuse it with fn. So this is going to be called a Boolean function. Okay? It goes from the hypercube. Here I'm not even referring to Bernoulli percolation. I'm just referring you take a function from the hypercube into 0, 1. There is no geometry here. Okay? And I want, for instance, to compute the derivative in P of the expectation of x. Where here, I refer just to the fact that the entries here, so it's a measure for which the entries here are ID, Bernoulli random variable of parameter P. So how do I compute that? Well, this thing is just the sum over every I from 1 to n of x of omega, for every omega, sorry, of x of omega, p to the number of edges in omega, 1 minus p to the n minus the number of ones in omega. So number of edges, I should prevent that from here. I don't have a geometry. But say omega is the sum of the omega I for I equal 1 to n. Okay? So this is just a definition of this thing. So when I differentiate, I get, I'm necessarily going to fail on this one, but okay. Do I want to do this computation? I'll give you directly the result. Okay, maybe I won't. So you get this. And this, if you think about it, is the sum for I equal 1 to n of the expectation of x of omega times omega I minus p. Just check the thing, and it doesn't give you that at all. So you add p1 minus p. I knew I should not have done it, but okay. If you do like that, it gives you the right thing. Something like that. So the p comes from this n here. If you divide by p, multiply by p, you get this. And well, if you disagree, just go and see Vincent. And I'm pretty sure he knows how to do this computation on the board. So, okay. So you get that. So what is the interpretation of this quantity? It's a covariance between x and the random variable omega I. Right? So it tells you how much the ith entry of your function impacts the whole function x. Okay? So this is called, I will call it here, the influence of the ith entry for the function x. There are a bunch of different definitions of this. Here it will be the most convenient one, I hope, for me. Maybe not for you, but, well, you should have taken the 2 first lectures. It will definitely be the simplest one for me tomorrow. So this is the influence, it's going to be our definition, the influence of our function. And therefore, we get this lemma, which is due to Margulis first and Rousseau as well, independently, basically saying it's, well, it's not a very deep result, right? But it's very useful, saying the derivative of a function x is equal to 1, a Boolean function f is equal to 1 over p, 1 minus p, times the sum for I equal 1 to n of the influences. So, overall, if I want to prove something like that, here I have a sum of influences. Here I have the variance of my Boolean function. So I need to prove that the sum of influences is much larger than the variance. And now we enter a new realm of mathematics, which is okay. Forget about the interpretation with Bernoulli percolation. Forget about everything. Just look at Boolean functions and try to bound the sum of inferences. So there is not even, you could forget that there is a parameter P. Just think you are at a fixed P. Try to bound the sum of inferences of a Boolean function in terms of the variance. And there is a beautiful theory that emerged from this question. So I'm a little bit stressed because one of the person is here. So one of the first results in that direction, trying to prove that the sum of inferences is much larger than the variance, is due to Can, Cali, and lineal. And that's the one I'm going to present in a second. I mean, it's basically the one that I'm going to present in a second, which is at 1/2. They prove the thing for the uniform measure on the hypercube. They proved that they had, I mean, they didn't prove that, of course, every Boolean function undergoes a sharp threshold because it's not true. You can take just the Boolean function which gives you, for instance, the output of the first coordinate. This one, the probability, I mean, the expectation is just P, so it doesn't undergo a sharp threshold. But you are going to see they have a very convenient criterion to check whether a sharp threshold a function undergoes a sharp threshold or not. The problem is that for us, we want to integrate the function on P. So we need a result which is true for every P. And this result is, so this is a KKL result. So the second result is due to Bourguin, KK, Katz-Nelson, and lineal. So I mean, the difficulty here is to remember the number of Ks. Because then they did all the good job. It's very nice to apply, which is exactly the same result for any P. And the last thing, because that's actually, I think, basically the one that I'm going to state here, it's a result due to Talagrand, which restates basically what they did, and appear a little bit later, but which is also good for us. So there are, like that, results, completely abstract, you are going to see. They are based on a different type of mathematics, which is Fourier, discrete Fourier analysis and hypercontractivity type arguments. So they are not referring to statistical physics at all. And they say the following. So it's kind of a very beautiful theorem. And I'm going to just state it a little bit differently. I mean, I just want something simple for me. So there exists a constant which depends on P. And forget this constant. I mean, basically, this constant is a nice constant, except when you are close to 0 or 1. But we will never apply it close to 0 or 1. And it says that the sum of, I mean, the variance of x, so for any x Boolean, and here I'm going to take it increasing. So, okay. Increasing, I should tell you what increasing means. For the partial order on this hypercube, right? So omega is smaller than omega prime if and only if omega I is smaller than omega prime I for every I. So variance of P is smaller than sum I equal 1 to n of inferences. And there is this constant in front. So if I just have that, I'm just saying the variance is smaller than the derivative of my function if I think of my interpretation here. So it's not telling me much. But the beauty of the theorem is that there is an additional term here, which is log of 1 over the inference. Okay? So this theorem is saying something quite funny when you first see it, is that your goal is to prove that you have a big sum of inferences, right? Well, this theorem is going to be useful to prove that when you know that all the inferences are small. Because if all the inferences are small, this term here is large. Therefore, if this term here is large, the sum here is much larger than the variance. So small inferences implies large sum of inferences. So in other words, I mean, but I really want to. I started 5 minutes late. I can finish. Right? Okay, good. It's better to ask before because the person first emerged from his notes. He doesn't know. He didn't have time to be upset at me. So perfect. Okay. So then I will explain to you a little bit more. So if you have small inferences, then you have large sum of inferences. Notice, for instance, that this theorem tells you something non-trivial. It tells you there is one inference that necessarily is not too small. Why? Imagine that all inferences are, say, so imagine inference I of x is smaller than n to the minus 1/2, say, for any I. Okay? So I don't have any inference larger than n to the 1/2. Then the log of 1 over inference is always larger than log n. I mean, 1/2 of log n. So in this case, the variance is always smaller or equal. I mean, 1/2 times log n times the variance is always smaller or equal to Cp times the sum of the inferences. So it tells you that one of the inferences is larger than log n over n times the variance. And that is, this log n was not clear a priori. If you don't have this theorem, by the way, it's quite simple to see that the sum of inferences is larger than the variance. Basically, you change like your random variables one by one, and you just check that the variance can be expressed, like it can be bounded by the sum of inferences. But here, sum of inferences larger than variance will only give you a C over n. Here you get a C log n over n. So it's a big improvement. This theorem gives you that max inference is larger than C log n over n times the variance. Okay, but you see, this doesn't imply at all that you have a sharp threshold, because in particular here, I told you it's true for any Boolean function. So let's try to see what happens, for instance, for x of omega, which is omega I, just the entry, the ith entry. In this case, what are the inferences? Well, the inference of any other I, any other entry, that was a poor I0, let's say. So the inference of any I which is not equal to I0 is the covariance between omega I0 and omega I. Because they are independent entries, it's 0. And the covariance between omega I0 and omega I0 is 1. So in this case, of course, you have one big entry, one big inference, but you have only one. Its inference is 1, so it doesn't tell you that the sum of the inferences is large. Okay? So historically, the way people used it to prove that you have a sharp threshold for a function at hand was to try to take functions which are symmetric under a group action acting transitively on 1 to n. Because in this case, if you take a function which is symmetric, then all the inferences are the same. If all the inferences are the same, because you have one of them which is larger than C log n over n, you get that the sum of inferences is larger than log n times your variance. And you got exactly the differential inequality that I erased, which was very smart of me. Sorry about that. So, okay, if you take an event which is invariant under translations, invariant under translations, then you get your C log n that I was looking for. So that was the idea of Bolobash and Riordan, who used it not for Bernoulli percolation, but for Voronoi percolation. I will maybe have time to discuss it tomorrow a little bit. So they use it in this context, and I could explain to you here how you use it. So the problem is that in order to use it in my context, I mean, crossing a box is not an event which is invariant under translations. Every single vertex, if you encode your box into the hypercube, so you label, say, your edges by integer between 1 and the size of your box, then your edges do not play symmetric roles, so you cannot use this Bolobash-Riordan clever argument of taking a symmetric event in this context. So they actually found a way around it. They defined your Boolean function that was symmetric. I don't want to do that. I want just to go back here and to just observe, and I will conclude by that. Don't worry, I will not go back, go over time more than that. I just want to go back to my function fn, which, remember, is the probability of crossing a box of size n times 2n. And I want just to apply directly this theorem here. Because it's not symmetric, I need to do something else than this Bolobash-Riordan observation that you can do it. So what I'm going to do is I'm going to bound from above the inferences. Prove that the inferences cannot be big. If I can do that, if I can prove that the inferences are all polynomially small, I'm done. I will get a log n. So let's look at what is the inference of an edge. So, of course, here it was on 0, 1 to the n, but again, here you could put, for instance, the edges of your box. It doesn't change anything. So what is the inference of this edge? How does this edge influence the existence of a crossing from left to right? Well, first imagine that you have a crossing from left to right that doesn't go through this edge. If you have a crossing like that, the state of this edge is irrelevant for the existence of the crossing or not. You can switch it, won't change the value of your function. So necessarily, there cannot be any crossing from left to right that doesn't go through the edge E if you want to have anything smart on anything non-trivial on the covariance. So necessarily, you need to have a dual path from top to bottom going through the edge E star. That's necessary. But on the other hand, imagine you have a crossing, a dual crossing, that doesn't go through the edge E star. Then changing the value of this edge won't help you either. In both cases, you won't have a crossing from left to right. So it also tells you that all the dual crossing from top to bottom have to go through this edge, which exactly means that you need to have a path like that. So for the edge to have a covariance with, for the entry here to be non-trivially correlated to my crossing, I need to have this picture. And in fact, when you have this picture, it's very easy to see that if this edge is open, you have your crossing. If it's not, you don't have. And you can just check that you get a P 1 minus P. The covariance in this case is P 1 minus P times this thing. But I'm not even going to use this P 1 minus P. I'm just saying, OK, the influence of an edge of this thing is smaller or equal to the probability at P of this. Okay? But if you have that, notice that in particular, one of these endpoints have to be connected to distance n over 2 in the dual configuration. Right? Either this edge is below half, and therefore it needs to be connected to the top, so it has to be connected to at least distance n over 2, or it's above, and it has to be connected to distance n over 2 at the bottom. So this is smaller or equal to twice the probability at P that you have a path to distance n over 2 in the dual configuration. But this is exactly the probability at 1 minus P of having a path in the primal configuration. the same because my dual configuration has Bernoulli parameter of parameter 1 minus p. But p is larger than 1/2, so 1 minus p is smaller than 1/2. And I proved to you that this quantity at 1/2 was polynomially small, so below 1/2 it's even smaller. So this is smaller than twice, n to the minus, I don't remember what I had put, but something like alpha, I guess. So I just proved to you that it is polynomially small, the inference. Therefore, when I put it here, I get that the derivative is larger than alpha log n divided by Cp, but again, Cp is some nice constant, times Fn, 1 minus Fn. And I can do my integration to prove my proposition. So it was maybe a little bit fast at the end, but anyway, all this thing was to try to give you a glimpse at how it was done historically in 2D, and then we are not going to do it, because in higher dimension, this sharp threshold theorem is very difficult to apply, because it's not clear to what you want to apply it. Crossing probabilities are not the right event anymore. So what we are going to do is we are going to develop another theorem to prove sharp threshold, and actually Vincent will explain to you for certain variables for certain Boolean function how you prove sharp threshold using it. And this other theorem is going to be the right tool to study higher dimension. Here, it's not how Keston did it. This thing, he really did it by hand, proving this sharp threshold. He really proved by hand an inequality of this type, actually with the n to the epsilon here. So what will we do in higher dimension tomorrow is first give you a simple proof by hand, completely independent of everything I did today. That will be my second lecture, and then Vincent will tell you more about how you really apply sharp threshold. Thank you very much.
Okay, are there any questions? So if not, let's thank Hugo again. So we're gonna have a 15-minute break. Hopefully there is coffee outside or in the coffee room.
Isso.